while we're doing this, while we're just reading through this small section in your notes, we're also going to be showing you how to insert these in your calculator. It's pretty straightforward, but we're going to use the equations from example 7 that you originally start off with, x equals t squared plus 2 and y equals 4t minus 1.
Why don't you just go ahead and write those down just real quick?
Okay, yeah, that's a good idea. This right here is what we're plugging in as we speak. And so big thing is to put your calculator in PAR mode and SIMUL mode if you're on an 83 or an 84 or 82. On the Inspire,
it just shows up. It's like magic.
Well, you have to go, instead of inserting a function, you insert a parametric equation.
And on Desmos, you just type what you want.
You just type what you want? Okay. The calculator will graph, if you do this on the 83 and the 84, it'll graph the equations at the same time, so that if we have an x1, y1, and then an x2, y2, it'll graph those all at the same time, so you can see like their pathways to see if they'll
if they cross or not,
if they cross at the same time, because that's a big deal. That's why parametrics are so important, is because it's not necessarily an issue if two things cross paths. It's an issue if they're there at the same time, because two things can't really occupy
like the other day
space.
When I was driving in my car. Maybe
we shouldn't talk about that. Yeah. A couple of nice tips. These again are for the 83 and 84s. That if you press clear draw when a graph is up, which is under the draw menu, it will redraw the graph. And so since we're looking at pathways that can be helpful. And then if you're in the middle of something graphing, if you press enter, it will pause it. Press enter again and it'll restart.
Pretty amazing.
If you press on any time on your calculator, it will just stop what it's doing. So if you press the graph button, you realize, oh, I put something in wrong, you can press the on button to stop it.
I picked a t-step with the smallest digits possible. This graph's taking forever.
Right, so you press the on button and move on from that.
Yeah.
You can, with the trace button, like trace the pathway, and it'll go by like t value. So if you're on one set of graphs and you're at like t equals 3, and you press up and go to the other set of graphs, it will show you where that graph is at t equals 3. So that helps you tell if they're gonna be there at the same time or not.
Right.
And so on your window settings for the 83 and the 84, it's in the it's just on the equation on the Inspire, like it's part of the X1,
it's part
Y1.
of the
You have the T-min, T-max, and T-step. So that's what values are we going to plug in for T, and that really matters. In general, a lot of these graphs will want something like -5 to 5 if they're just equations. But if it's real life, it's a lot more likely that you'd want like 0 to 10 or something.
For example, you don't count a rocket launch basically until it launches. Until it launches, which is at time 0.
And so
sometimes they don't launch well.
Sometimes they do, sometimes they don't. And so the T-step part of that is if you put in like from 0 to 5 with a T-step of 1, it's going to plug in 0, it's going to plug in 1, 2, 3, 4, 5, and those are the only values it's going to plug in. And so you can get a graph that would like look really like
jerky.
Yeah, jerky.
Not very smooth.
Not smooth. But if you lower that T-step to a smaller number,
like 0.01,
then it's going to be a lot more accurate as you go. And so it's kind of tough to find a balance between, I want the smallest T-step possible without having to wait forever.
But I don't have all darn day to graph this sucker.
Right. So you may have to mess with that some. And that's where that on button trick really helps, because if you start graphing, you're like, that's going to take forever, then you can just change it a little bit. So 0.01 to me seems like a pretty good one most of the time, unless you just have a ton of t values.
Unless you're going like to infinity or something. Infinity. Infinitesimous.
All right, 2 trains
are scheduled. Not this question.
Whatever. 2 trains are scheduled to leave Chicago on parallel tracks. The first train will leave at 12 noon, traveling east toward New York City, a distance of 850 miles at 50 miles per hour.
It's like a Sunday drive pace.
Yeah. The second train will leave for New York City at 1 p.m., traveling at 55 miles per hour. Write a set of parametric equations for each train. So train number 1.
We could call it T1.
We could, but that might confuse us with our other T's.
Okay, all right.
Okay, so what happens here is we are only concerned about the horizontal situation, like they're talking about parallel tracks. So we're going to end up with two lines that are going horizontally
at the same time.
Maybe. So for y1, we just need to pick a value, any value, so that it's just going to go along at a certain y value. And so I'm going to pick 2 because I just think that's a cool number to pick.
It's not,
It's a good one to pick.
Right.
The x is going to have to do with our speed. So 50 miles per hour means that we would be traveling at 50 t,
50,
right?
Yeah, 50 t.
50 t.
Because t would be, in this case, time.
Right, and so then train 2.
So they're going just a little bit faster. They're like the young Sunday driver. They're a little quicker than Grandpa Sunday driving.
And so for this one, for my y value, I'm going to pick something like 4, and then whenever I graph it, we'll be able to see them separately.
And if you're doing it simultaneously, you can watch them go at the exact same time.
It'll actually look like a little race. It's really neat.
Yeah, a little race.
So my x2, I'm going 55 miles per hour, but I'm also leaving later. I'm leaving an hour later. So how do we put that in there?
Gee, we say has it got to be t-1, right?
Right, and so...
Because it's not at the same time. The other one is already an hour in, so we're an hour behind.
Okay, so should we just do -1?
Maybe in parentheses.
Maybe in parentheses? Because we're saying the time itself has to be subtracted by 1?
Yeah, because this guy doesn't actually get started until the second hour of the other train.
Right. Which would be 55t minus 55. So we would plug, and so how about, let's talk about windows. So for our x's, we would want 0 to, how far is it to New York City?
850 miles.
850.
You know, and on your step on that,
your scale,
you probably want like 50s.
Yeah. And then for y, we just need to be able to see 2 and 4, so I would go something like 0 to 5. 6.
Yeah, 5 or 6, yeah, perfect.
Something that you can really clearly see.
The scale on that one can be 1.
Yeah, and then for our t's, we know that we're starting at time 0, and then we would basically kind of approximate like how long do we think it's going to take. And so I think it's going to take under 10 hours for both of them.
I was going to say like 500 hours.
That would probably be a lot.
Okay. So let's try 10 and see what we get.
So let's try 10.
Okay.
Fortunately, there's this formula that we use, d equals rt, that we could actually figure out.
We could always change the t if we need to.
We could. So our t step, we could use we can try 0.01 and see how long that takes us. So I'm going to plug this in over here and we're probably plugging it in right now.
Yeah, we're showing you what's going on because we're cool like that.
So 50 t.
These rockets are amazing.
Are the rockets still going?
Rockets are still going. You know, they go up, they come down. Some of them come down with a little bit more excitement than others.
Yeah, that's true. Definitely true. So you want to talk about what's happening on maybe A?
So on train A is just traveling around.
No, not train A, on part A.
Oh, how long until the second train overtakes the first train? Well, basically what we have to do is we have to figure out when do those two guys cover the exact same distance. And if we're trying to figure out the exact same distance, that's the x value for both of those, right?
Right.
Right. So if we want to know if we want to know the instant when the second train catches the first, we could just set the x values equal to each other.
Okay.
Solve it for t.
All right.
How does that sound?
Let's try it.
Okay.
So the t equals 0.01, I'm noticing is a little slow, and it didn't go all the way. So maybe we need to pick a different, maybe we need a bigger than 10, maybe like 20.
50 times 10 is 500, and we've got to get to 850. So what if we did 20?
Okay, I'm going to change it to 20. I'm also going to change it to 0.05 and see how that helps, if that helps. That's quite a bit faster.
That's quite a bit quicker.
All right, so we're setting our x values, our x equations equal to each other because we want to know when will their coordinates be the same.
Yeah, their x coordinate, as it were.
So guess I can do that.
Use the second
Distributed.
equation there. Yeah.
Sorry. So we want to get the t's together and the numbers on the other side. So
Right.
that's going to end up being 55 equals 5t, because I'm going to subtract 50t over and add 55. So then I divide by 5 on each side, and that gives me t equals 11.
So 11 hours into the trip,
Right.
train 1 will catch train 2.
Right, and if you have this on your calculator, you could actually go to t equals 11.
Just hit the trace button, or you
then-
could just hit x equal, type in 11 on sometimes.
And if you switch between the two graphs, you should see that at t equals 11,
Wow,
they are
they go
both
this.
at
They're
5:50.
identical.
Yeah, so at 11 hours. And so then it asks how far are they from Chicago, which is where they left. So that's
Well,
why it's...
that means you traveled for 11 hours.
And the first train was at 50 miles per hour, so
Right.
50 times 11, that's 550
Well, how did you
miles.
know that? Did you do that in your head?
Yeah, totally.
You're brilliant.
How long will it take for each train to reach New York City? Well, the first train would take 850 divided by 50.
Because it's got to go that far.
Right, you've got that distance
I got
over
that
that.
right here. 17 hours.
17 hours.
17 glorious hours.
Okay, and then the other one is 850 divided by 55.
15.45 hours.
And so, and that's just from the time it leaves.
Shouldn't
It'll
that be
take it
850 plus 55 divided by 55?
Why would it be 850 plus 55? Well, like our... What
Oh,
is-
no, never mind. I'm good.
Okay, so we're just saying from the time that the second train actually
Right,
starts,
right,
it'll take
right.
almost 15 and a half hours. How much would the train have to increase its speed so that it would arrive in New York City before the second train? Now, we can basically do like a guess and check kind of thing on our calculator where we go in and we into the y values, and on the first train we can change it like to 51 and then see if that makes it, and just watch it and see if that makes the first train get there faster. So I'm looking at it.
Oh,
no,
that's really close,
it's really
but not
close. So
quite.
I'm going to change it to 52. So first train, still in the lead.
52 is close, but
52
not
is close,
but it's not
really,
quite.
we'd probably do like 3 miles per hour just to be sure. So increase by 3 miles per hour.
And there's a bunch of really super fancy math we could do to do that. But
Yeah.
you know what? We've got a calculator that we can use for a very good estimation. Why not use it?
Why not?
I agree.
Okay, we've got quite the problem here. You may have noticed it while flipping through that we've got this paragraph, and then on the next page we've got an A through I to fill out. So we're just going to walk you through a situation like this. And
I'm recovering. I'll be there in just a
yeah.
second.
So example 9, Bugsy and Mugsy, an unexpected journey. So while working on the computer, Chris observes a bug walking on the screen of the monitor and traveling in a straight line until it leaves the screen. Chris knows that the rectangular screen is made up of little square units called pixels, and his screen is 800 pixels wide by 600 pixels tall. So here we have a graph that represents that 800 by 600. Notice that the scale is not the same each direction. On the bottom, every line represents 50. Going up, every line represents 25. So that is going to be important here in a second. Suppose that Bugsy enters the left side of the screen 100 pixels up from the bottom left corner, and that at the end of each second, Bugsy has moved right 2 pixels and up 3 pixels from his position at the end of the previous second. Well, skipping ahead, at the end of this, we're going to have to sketch the path of... Oh, wait, no, not skipping ahead. Right there.
Don't
sketch
skip
the
ahead.
Sketch the path of Bugsy. So he starts at 100, which is right here, and then at the end of a second, he will have gone up 3 and right 2. Now,
Up 3, right 2.
Now, because of my scaling here, I'm going to go up 3 50s. Okay, so I'm going to go up here. This is 1, 2, 3. I'm going to go up by 50s. And then if I go right by 50s, that's just 2 lines. So that gives me a place right there.
Right.
And then I'm going to use my straight line tool that I have. You should just go ahead and maybe plot some more points, and then
you want to get
do
as
your
many accurate points as possible. And also, just a little word of caution here, the reason that we're counting by 50s is because the scaling on both the x and y axis are not identical. So when
Right.
you're going for that slope, you want to have
You want them to be identical. And so, but we've already got this graph here to use, so we've got to
Right.
make it work.
That's okay, and we can make it work because we're geniuses. So.
Right. And it does say to clearly indicate the starting position. He starts over here at 100, and he's going to the up,
Right.
up and right. Now let's talk about Mugsy.
Mugsy.
Simultaneously with Bugsy, a second bug Mugsy enters the right side of the screen, 150 pixels up from the bottom right corner, which would be right here.
Right, at 150.
Uh-huh.
Yep.
And
Looks
then
good.
at the end of each second, she's moved left 4 and up 1. So if we loop,
count in 50s.
so this is 1, 2, 3, 4 50s, but when we go up, we actually need to go up twice. Because we're going up a 50, which
Right.
is 2 lines.
So that our slopes are correct.
Right, and if I keep going with this,
3, 4, and then up 2 50s.
I'm going to run into the y-axis. And that might be helpful for us to be able to,
Bam, right at 350.
find the y-intercept at some point during
Thank
this problem.
goodness.
All right.
We got to that point
Yeah.
on the y-axis.
All right, so...
So we started, now we'll clearly label where we started though, Mrs. Stevenson,
Okay, so
because
we
it's
start,
right there. Yes,
Mugsy
okay,
starts
there we
here.
go.
Okay, so it asks us to sketch the path of Mugsy and everything. We did that. Now we're going to work out some problems. So first we want to fill in this table. And so at time 0, Bugsy is at his starting position. And his
Right.
starting position is what?
0, 100.
Right. Okay, because that's over here.
Right.
Now, we drew our next point way up here, but after a second, how far will he have actually moved?
Well, he's only moved to the right 2 pixels and up 3. So
we
if you
would-
go right from 0, 2 units, that's 2.
Right, and then if I go up
and
3
then up 3
from
is
100.
103.
And so what we can do is we can continue this down. Every second, he's going to keep going right 2. So this would be 4, 6, 8, 10.
Right.
And every second he's going to go up 3. So
So
that's
it's-
106,
yep.
109, 112, 115. And you could keep going. We just decided to have this
Yeah,
much.
like that's where we're good.
All right, so where's the starting position of Mugsy?
So, okay, Mugsy actually starts way over on the other side of the screen. So his actual x coordinate is 800.
Right.
And he starts at a y coordinate of 150. So that's his starter.
Right.
And then he moves 4 units left
Every second.
every
so
second.
we need
So-
to subtract 4.
So, right. So he's not going to 800 4. That's not on the
That's
screen.
not the right way, no. So subtracting 4 each time gives us these values. And then for his y, he's
For the
going...
y's, now he's going up 1 unit every second. So that's pretty easy. 151,
Yeah, it's like counting.
152, 150, whatever.
Note to self, Hazelwood can only count to 153. 'Cause-
Did I get to 153?
I don't know,
I think I stopped at
152.
152.
Yeah.
So, yeah.
All right, so we're going to use this, and I'm sorry for the unfortunate page flip that you've got going on, but we're going to use this to fill in A through I on the next page of your notes. So here we go. First off, write 2 sets of parametric equations to model the information in the table for Bugsy and Mugsy.
Sounds easy enough. 1 for each color.
Okay, so we start off with Bugsy. So we could call it X1 or we call it XB.
Hey,
For
XB.
Bugsy. And so if we look at just the X values, that we've got 0, 1, 2, 3, 4, and 5 for T. We've got 0, 2, 4, 6, 8, 10 for X. We're basically trying to make an equation out of
Right.
those 2 things.
I feel like we're doubling T.
We're doubling T. Every time that we go a second, we have twice that much for
Right.
X. So we would have 2T. We could also
Okay.
think of this like a slope-intercept kind of thing.
Oh,
That
slope-intercept,
we're
nice.
starting at 0, so it's like a plus 0, and then we're adding 2 each time.
That's good.
So
That's a good way to
2T.
think about it, too. Okay.
And so
The y
that's
coordinate then.
helpful for YB, because for Y, we've got
Which
that
we start-
same T column,
Right.
0 through 5, and then the Y column starts at 100 and goes up 3
Right.
every
So
time.
so we got to be 100 plus,
Right, so 100 plus.
and then 3 every time we move.
And so every time that I add a second, I should
Right.
be adding 3.
Right. So there's the, which one is that one? Bugsy.
Bugsy.
There's
That's
the Bugsy parametric equation right there.
Now
so
let's do Mugsy.
let's do Mugsy.
So now
Mugsy.
we are looking at, I'm going to sneeze.
Say cheetah.
Okay.
Did you say cheetah?
I didn't. No, it went away. So now we're looking at the 0 through 5t column and the x column for Mugsy. So we've got that starting point is 0, 800.
Yeah, so now this is going to be 800, but we're going to move left, which is a minus
Right,
sign.
so every time we're subtracting 4, so that's going to be minus 4t.
Yeah, I like
and
it.
then y, Mugsy, is we're starting this time with 150.
Right, but we're adding still, because we're going up the screen.
Right, we're adding 1t every single time.
Right.
And hopefully this makes sense because you may be inclined somewhere in here to have like 3/2 or -1/4. Those are the slopes of those lines, and we'll use that later.
It's coming.
As far as the parametric equation goes, like we split those up into their x parts and their y parts.
Right, and that's what a parametric is. It does all the splitting of the stuff.
Absolutely. B, give the location of Bugsy in ordered pair after 20 seconds, 25 seconds, and after 50 seconds. Well, we just have to plug in, right?
Yeah, that's the t value there. So in order to get the actual ordered pair, what they're saying is t has to be 20. And so everywhere you see t for the Bugsy equations, you just put a 20 in there.
Right.
And by the way, you will never get a point of just an x value, of just a 40, or you'll never get a point of just a y value, which in this case would be 160. You always get a point with x and y.
Which is why it's kind of giving us a hint that our answer should be an ordered pair there.
Right.
So after 20 seconds, Bugsy should be at the point on our graph 40, 160. And then we're just going to continue plugging in. So for 25 seconds, we just need to do 2 times 25, which is 50. And then 100 plus 3 times 25.
175.
Right.
And remember, this is an ordered pair. This is not just an x and not just a y. They go together to tell us exactly where we're located on the xy coordinate system.
Absolutely.
That's right,
and
absolutely.
then 50. 2 times 50 is...
Hundy. It's a hundy.
100, like the car?
Yeah. I wasn't thinking of the car necessarily, but hundy.
250.
Like 100, it's a hundy.
I think you're the only person I've ever heard say that.
Gosh, you never watch Wipeout.
Oh, I've watched it a couple times, maybe. After how many seconds will Bugsy leave the screen? So let's think about what that's asking us. Bugsy leaves the screen.
At the top of the screen.
At the top of it. Let's go back and look at our graph.
See, that's the green line.
Up here. Right up here is what we're looking for. We're looking at where is he leaving? Is it where or when?
Where? I believe it's where.
After how many seconds?
Yeah, so we have to figure out when the y coordinate then is equal to that, because the next step he takes, he's off the screen.
Right. So we want our y for the parametric equation to equal 600.
Right. 600.
Yes.
Okay.
Exactly. So 600 equals, and we're going to set it equal to our y equation, 100
for
plus
Bugsy.
3t. So to solve, I'd subtract 100. You get 500 equals 3t.
Well, and in a real world situation, maybe in a real math world situation, we would do 500 by 3 and be like, oh, that's the answer. But if you were to ask me, Mrs. Stevenson, how long is 500 thirds seconds?
I wouldn't know.
I wouldn't either. So in this case, let's go ahead and just figure out a decimal that we can actually use. 500 divided by trace. My calculator said...
Control enter.
Control enter. It's 166.6 seconds. So this bug's really taking its time crawling across the screen.
I don't know. That might be pretty fast. It depends on what kind of bug,
3 minutes.
Right? Well, okay, yeah, sure. Okay, so after how many seconds will he leave the screen? After 166 seconds.
Right.
At what location does he leave the screen? Well, we know that he's leaving it at a y value of 600 because we looked at our graph and we said, well, he gets to the top.
Going off.
So we need to figure out now what the x value for that coordinate is, and we can figure that out if we use what we just did, that 166.6 seconds or 500 over 3.
I think the 500 over 3 will actually give us a more accurate answer because we don't have any rounding issues with that.
That's true. So if we go back to our x equation and we plug in our time
of 500 over 3,
then we get 1,000 over 3, which is so much better than 500 over 3.
I know exactly what to do.
Okay. Control enter. Bam.
333.3 for the x coordinate.
Which I didn't really leave myself enough room in that. That was unexpected.
Unexpected indeed. But anyway, that's the coordinate position at which time this guy is off the screen.
Let's go back and look at the graph real quick and see if that's right.
Let's see if that makes sense.
333. Yeah.
You know what? It looks pretty good.
That's so exciting that that's right.
That's
okay. Let's go.
Next one, right there.
All right.
Okay.
Part E. Give the position now of Mugsy after 20 seconds. Okay, so here I just really quickly wrote our equations up here for reference. So give the position of Mugsy after 20 seconds. So we take the Mugsy equation and we plug in 20. So that's 800 minus 4 times 20, which is 800 minus 80, which is 720. And 150 plus 20, which is 170.
Right.
So 720, comma 170.
X then Y, always in that order.
Yes.
Yeah.
So after how many seconds will Mugsy leave the screen?
Well, now Mugsy this time, he's going all the way across the screen from left to right. He actually exits the screen at a Y coordinate of 0.
He does.
Okay. And so
a Y coordinate? I think you mean an X coordinate.
I meant an X coordinate.
And actually, because of our graph, we actually
we
technically
do know the Y coordinate
point
as well.
So we just would have to pick either one. It's safer to pick the X value in case we weren't 100% accurate.
In case we're not right on that 350 marker. So let's go ahead and use 0 for the X coordinate.
Okay, so we will plug in 0 equals 800 minus 4t.
Right.
So we can add 4t over and get t equals 200
seconds.
Oh,
these are some slow crawling bugs in my humble opinion.
Maybe they're like those really slow moving like beetle thingies. Maybe they're ants that
maybe they're snails.
So tiny. But is a snail a bug?
I don't teach science.
Okay. At what position, ordered pair on the screen, will the paths of Bugsy and Mugsy cross?
Now look, we see that they're going to cross, but this could be like the whole stop sign intersection sort of thing. They might not cross at the exact same time, but they might.
They might. So the first thing we got to do is figure out where they cross, so that then we can figure out what time each of them get there.
Right. Now here's the thing with this: we need to know the exact X and Y coordinate, not just the X coordinate and then just the Y coordinate. We need the whole. Everything needs to match here.
Right. So what we have to do, unfortunately, is come up with a normal slope-intercept equation for each of these.
Right. So
we're basically eliminating the parameter, but because of all the information we have in our table and on our graph, it's actually there's an easier way.
It's not bad.
You can remember you can use point slope. We know the slope for both of these. We mentioned it earlier.
Right.
Okay, so you can use point slope and help you get the equations, or you could use just the table and maybe a little like thought process.
You know, and on this one, I think you could also use slope intercept as it works out for this particular problem.
For this one, yeah, we were able to see the y-intercepts for both of them. So for Bugsy, it has a slope of up 3, right 2, and it has a y-intercept of 100.
Of a hundy.
And for Mugsy, we've got a slope of, we're going up 1 but left 4, which is negative 1/4. And then if you look at your graph, if you drew it accurately, you can see that it's at 350.
350. He crosses the y-axis at 350. So we can actually use these two things together
now
to help us figure out where that actual point of intersection is.
Right. We're solving this system of equations, which I think is something we recently did.
You know, you could use a matrix.
You could use a matrix. That seems a little bit overboard. We could use substitution or elimination.
You could use an inverse matrix.
Let's use substitution
you
because they're both y equals.
Gaussian elimination.
You could graph them.
You could do reduced row echelon form.
I'm just going to set them equal to each other. Is that okay with you?
You could use substitution.
Okay, let's use substitution.
You could use
That's a great idea.
Elimination. You could graph both of them.
Yes, you could. And that would be pretty easy since they're both y equals. So here, to solve this, I would multiply by 4 personally and get rid of my fractions. And so when you do that, you have 4 times 3
You got to multiply both
halves,
sides of that equation by 4. So when you, this is a good trick. This is a great trick, actually, to have in your bag of tricks for solving an algebra problem. Just remember to do it to everything.
Yeah. So that's going to be negative x,
Yep.
and then 4 times 350.
4 times, I'm on it. 4 times 350.
Is that 1,500?
It is 1,400.
1,400. So then we want to get our x's on one side and our numbers on the other. So I'm going to add x over and get 7x equals, and subtract the 400. So that's 1,000.
Oh boy.
So x equals 1,000 over 7.
I get 142.857.
All right, that's our x value. We got to plug it back in somewhere up here to get our y value.
And when you plug it back in, use the 1,000 over 7 part so that we can get as accurate as possible.
Or keep it in your calculator and just...
Or keep it in your calculator.
So if I do that, if I times 1,000 over 7 by 3 halves and then add 100, what do I get?
3 divided by 2 times 1,000 divided by 7 plus 10. Oh, plus 100. It's 2,200 over 7, which is 314.286.
Okay, so that's our ordered pair, 142.857, comma 314.286. Should we go back and look and see if that looks right?
Let's do.
142-ish, 314-ish.
So 142,
314.
314.
Yes!
Yes.
That looks right.
that is
That's so exciting.
Thank the heavens.
Okay, so we got their point of intersection. Now we need to know when each of them cross or get to that point.
Right.
So that means that we have to use the parametric equations.
Back to parametrics,
That's where our
right.
time is. And
Right.
so we need to take either x or y for each of them and set equal to one of these 2 points.
Right.
Okay, because what should happen is 2t equals 142 and 100 plus 3t equals 314. Those should give us the same values for t.
Yeah, it doesn't matter which one you pick.
So pick maybe the easier one.
I think the easiest one to pick out of all of this for Bugsy is for Bugsy, and it's the xb equals 2t. Like that's
the easiest thing
yeah,
ever. You just
like
divide
for
by
sure.
2.
Yeah.
Divide by 2.
Oh, all right, I'm on it. Divided by dose. 71.4286.
All right, 71.4286.
That's how many seconds it took
That's how
for
many
him
seconds.
to crawl to that spot.
And let's give Mugsy a look. So I'd go with the second one.
I'd go with the Y one, yeah.
So 150 plus t equals 314.286. So subtract 150 over.
164.2857.
And so we didn't have to necessarily write all those decimals down, but
No.
now we come to part I. Will they collide? No, because
They get there different
they're
times.
completely different times.
Right. Not even close.
No.
So if one of them is like the insect of prey, then he missed his meal.
Yeah. But if they, were lonely bugs and were hoping to go out on a date,
right?
Then they missed out.
Then they got at the same place at the wrong time. That
Yeah.
reminds me of the first date I ever had with my wife, which I don't want to talk about right now.
I don't want you to either. So let's just projectile motion. That's when you throw something or
Launch it.
launch it, when you project something.
Physics people will love this kind of stuff.
Right. So when you throw an object, its path can be modeled with a parabola because, especially if you throw it up, like it's going to go up and then come back down.
Mm-hmm.
The general formula for this using parametric equations is this set of equations right here. And then in that, V sub O, that's the initial velocity.
V naught.
V naught, you could say. Theta is the initial angle that you're projecting at, and h is the initial height. So we've got an example here where the first thing we want to do is write a set of parametric equations that models the motion of a kicked football.
Wow. That's are we talking the punter for the Edmond Memorial football team is in old school football, as in what the world plays, or is that American football?
I think it's talking about the Edmond Memorial football team.
So the soccer football team or the
No,
football,
the football team.
football team?
Isn't it the football team? We're trying to punt.
The goalie punts and Okay.
All right, so x equals, in the paragraph here, we've got information. Our initial velocity, our v naught, is 85. Our initial height is h. Our theta is 35, so we just got to fill it in.
That doesn't sound too tough.
No, not tough at all. Keep in mind
Now,
this is in degrees.
I was just getting ready to say, how do I know what mode for my calculator to be in?
Well, all you got to do is look
Call
at the degree.
Ghostbusters?
So these equations actually come from a very physicsy thing, like breaking up the x part of the motion and the y part of the motion. That's why cosine is with x, which if you remember anything from our trig stuff this year, hopefully you remember that x and cosine go together, sine and y go together. And then in the y equation, we also have to add in the fact that gravity is working against the ball. And that's where this negative 16t squared is coming from.
Yeah, hold it down. Keeps
Yeah.
it from going into low Earth orbit.
Yeah, so this right here is our set of parametric equations that models the motion of our football. That's part A. We're going to look at the rest of this stuff on the next slide here. Oops.
Pick it. There you go.
All right, so I just copied those over so I can
Sketch
refer
the
to them.
graphs.
We're going to sketch the graph. So go into your calculator in parametric mode. Make sure you're also in degree mode, and put in that set of equations.
Enjoy a starburst. Yeah, sorry. I had to clear off the old graphs. All right, so here we go. 85 cosine 35t. It's cosine 35 times t. And negative 16 t.
Did you need a degree symbol?
T squared. No, I think I have it set for degrees.
Okay.
We'll see in 1 minute, won't we?
Mm-hmm.
But I thought I picked degrees. Plus 85 times sine 35 times t plus 2. Bam. And perhaps I picked incorrectly here. Let me just double check these.
That's a terrible thing to have happen.
That was that was horrible.
That's,
1
that
minute.
was the worst.
1 minute, please. It says I'm in degree mode here, so I don't know what the heck. $85 times cosine 35t. 16t squared plus 85 times sine 35t. Let me just this is weird. Well, that made a difference. So apparently I needed to put the degree symbol in. You were right, of course, like always. Now, I need a good window here, so...
Well, we only need positive x values.
Right.
So, like, from 0 to, I don't know, like, 250?
250?
You want to try 250?
All right, we'll try 250. And the same for the y-axis.
Yeah. And that'll just give us an idea if we're even close. He picked a y of 100.
100's a little big, so maybe 75 or 50?
Okay, change it.
Yep. 250 is good on x, so I'm going to try 50 for y. Oh, it's perfect. Well, after all that work, I need a candy. After this lesson, I need a candy.
All right, so we've got this parabola, and ish. Okay, it doesn't have to be super accurate, but we know that our x values need to be like a good window is between 0 and 250.
Mm-hmm.
Our y values
0 and 50.
from 0 to 50. His t values were automatically set to go from 0 to 2 pi, and that seemed to work out fine. And his t step was like
Let me check on that.
Something.
Yeah, 0.13, yep.
So now that we've got this sketch, it will help us think about some things. For example, when we are asked what is the maximum height reached by the football, they're asking us to find this point. Now, I don't know about on the Inspire, but on the 84s, it won't let you calculate that point.
You know what? I'll just check real quick.
Okay, so the idea here is, when is our y value going to be the biggest? So let's look at our equation for y. And let's think about it by itself. If we just have this equation for y, what kind of equation is this? Well, that itself is a parabola. And so we could go back into our rectangular mode and graph this with x's instead of t's and calculate the max of that parabola.
Right.
And that will tell us what this maximum height is.
We could take a derivative and set it equal to 0.
We don't know how to do that. We're not in
Okay.
calculus.
All right.
So why don't you...
I have an idea.
Yeah?
If this is a uniform parabola, couldn't we just take the x coordinates and look at the halfway point? Like maybe find where x equals 0 and go halfsies? Just tossing it out there.
I guess we could.
I can graph the other one too.
Okay.
So I'm graphing us negative 16t squared plus 85 sin 35 degrees. Not forgetting that guy this time.
Yeah, good call.
X plus 2.
All right, so he's putting him in with x's here instead of t's so that we can look at that kind of parabola. Now that parabola...
Changed my window now.
Yeah,
I gotta
now
change my window.
Because now that's going to be a little parabola tiny in the corner.
So 50 is still too big, but we can see...
But we can find the maximum.
But we can find the maximum.
So you go to second calculate and go to maximum.
Yep.
Or on your Inspire, you go to analyze
graph and max.
Pick left bound, right bound.
Lefty, righty. Okay, here's what I get. I get the coordinate of 1.524, 39.14.
Okay, so let's think about what that's telling us. That's telling us what the maximum for this is, where our x's were really t's,
right,
and our y was really y. And so that means the maximum height reached by the football will be 39.14 feet. We want the y value. We want what's the biggest our y values can get to.
Right.
And if it asked us what time that happened, it would be at 1.524.
Right.
But it doesn't ask us
Doesn't
that.
ask.
So now it asks when and where will the football hit the ground. Now, you mentioned the whole, if this is a uniform parabola, then we should be able to split this in half. And so we actually could use that, because if at halfway it took 1.524 seconds, then if we multiply that by 2, then that should give us how long it takes before it hits the ground.
This is 3.048.
It's what,
3.048.
48 seconds. Okay, so that's how long it takes. And then we can plug that into our x equation to figure out what this, we're asking, where is this point right here? What x value is that at?
Right.
So we'd plug it into the x equation. I didn't think of that when I originally worked this, and so the way I actually did it was I set this equation equal to 0, which I think is what you were, you said something about, maybe, I don't know. Because whenever you were talking about finding where it hits and doing half or something like that.
Right.
What am I doing? 3.048.
Oh, 85 times cosine degrees times 212.226.
And that makes sense considering what our window was. That seems about right. So that's feet. And that's it. So for problems like these can be really difficult, but you got to break it down and think, okay, is it asking me where the x value is? Is it asking me where the y value is? What is it a maximum? How do I find a maximum? You know, things like that.
Stuff like that.
All stuff we've done before.
Indeed.